Greetings, everybody. Let's take a look at this problem that you see up here. And I've copied this, the way that you would see it on the assignment. This is the way that it reads. It comes with this diagram. And then we have these two questions and their answers. Now, I'll let you read this if you want to, and I'll explain it my own way. So basically, I want to get from here where it says start to here where it says end. And this distance is 5, and this distance all the way across horizontally is 7. Now, the scenario is that I'm going to get from start to end by traveling by water over the length A right there. And I'll be rowing a boat at a certain speed. And then I'm going to land on the shore at this point right here. And then from here to the ending point, that's the length B, where I'll be walking. So I'm going to row and then I'm going to walk at different speeds. Okay. And the goal is where along the shore, so this horizontal line right there is the shoreline, where along the shore should I land so that I minimize my travel time? Okay, so that seems kind of weird, but if I'm going to go from here to the shore and then walk the rest of the way, and I row at one speed and walk at another, then there might be like this exact point where you land along the shore that minimizes the total travel time. Okay, so that's the scenario. All right. Now you can see that given over here if you want to, and you can read about it, but that's just my diagram and summary of it. Okay, so like I said, part A right there, length A, I'll travel by boat. The speed that's given that I'll travel is 2 miles per hour. The distance I'll be traveling, well, let's see. So by that diagram up here, this distance directly to the shore, considering that the shore is a straight line and we travel directly to it at a right angle, that's 5 miles. And although it says the distance from that point directly to the shore to our destination is 7 miles, I'm going to have to break that up because at some point I'll be landing on the shore and I'll have like two distances to keep track of. So I'll say like this distance and that distance have to add to 7 because that was the total distance that was given. So I'll say this one's x and that one's 7 minus x. Is that consistent? What is x plus 7 minus x? It's 7. Okay, so I could break it up that way. So I'll say this. I'll say, okay, the distance that I'll be traveling by boat is the hypotenuse of this right triangle, which is 5x in A. Okay, so that's going to be square root of 25 plus x squared. All right, now, so here I'm just trying to get some details on paper. At that point, it occurs to me that my goal is to minimize the travel time. Like where along the shore do I land so that the travel time is a minimum? Okay, so I'll need to, out of some of this information, somehow express the time. Like the unknown in all this is where do you land along the shore? And that's given by this x right here. I could say it's like x miles from that point or something like that. So how do I express the time out of that? Well, so it generally distance is rate times time. If like say the rate's constant and all the rates are constant here. And I can solve that for time. I can say time is distance divided by rate. So see how I said, well, there's length A right there. I know the speed I'll be traveling along that length. And I also know the distance. Well, so because of that, I know the time. It's going to be distance divided by rate. All right. So that's how long it's going to take me to travel along that length A right there. What about B? So in B, we'll be walking. The speed that we'll be walking was given to be 3 miles an hour. The distance is 7 minus x. Remember I chopped up this entire length of 7 miles into x miles and 7 minus x miles. So the distance is 7 minus x. And the time is that distance divided by the rate by this. Okay. All right. So I've divided my journey up into two parts. And I know the time it takes to travel along each part. Okay. Now my goal is to minimize the total travel time. So let's write a function of this distance x that gives me the total time. And that would just be this number, root 25 plus x squared over 2, plus this one, 7 minus x over 3. Okay. All right. Now, my goal is to minimize the total travel time. And I have a function that measures the total travel time. So I can find the minimum on that function by finding the derivative and setting it equal to 0. So here's your derivative, which involves the chain rule. You know, I see that divide by 2 right there. I factored that out. And this is 25 plus x squared to the 1/2 power, which I brought to the front. Then I subtract 1. And this is the derivative of that inside part, 2x. Okay? What's the derivative of 7 minus x over 3? Well, I broke that into 7/3, which is a constant, minus x over 3. Okay, so the derivative of 7/3 is 0, minus the derivative of x over 3 is just 1/3. So there's your derivative. Here's your total time function. Here's its derivative. And then there's me simplifying it. This 2 cancels with that 2. It leaves me an x on top, a 2 on the bottom, root x squared plus 25. Now, let's see about solving that for 0, finding a critical number. So if I take this and set it equal to 0, I might immediately move that 1/3 to the other side. I cross multiply and I get this. I square both sides in order to solve by x. Okay. And then I eventually chase it down to root 20. And if you want to simplify that, to root 5. Okay. So, all right, here's what you need to do. If you want to minimize your total travel time, this point where you land on the shore and walk the rest of the way from there is 2 root 5 miles from this point right here. Okay. That distance x for minimum travel time is 2 root 5 miles. Now, is that the answer though? This might be the number for x that minimizes your travel time, but there are lots of things somebody could ask me about this regarding the minimum travel time. So I'm going to go back up here. So it says, at which point on the shore should she land to minimize total travel time? Okay, so then I read a little bit further, and it says to minimize total travel time, the boat should land how many miles from the restaurant? Now in my diagram, this is the restaurant. So we're trying to get from here to there. It was a crazy journey of rowing a boat some of the way and walking the rest of the way. So it's actually asking me for how far is it from that landing point to that end point. Okay, that's what this is. So my solution for x here isn't actually the aspect of the situation that I'm being asked for. Okay, what I'm being asked for is how far is it from here over to there? How far is length b here? Well, that would be 7 take away whatever the x is. Okay, so all right, how far is the landing point on the shoreline from the restaurant? 7 minus x was that distance from the beginning. I just found x to be 2 root 5, so 7 minus 2 root 5 miles. I noticed in the question it says give the exact answer, use radicals, so no rounding or anything. So I get right away 7 minus 2 root 5. I see the answer given in my math lab, like the correct answer they're presenting to me is 7 minus 10 over root 5. But that's the same number. You take their number, rationalize it, and you'll get my answer. Okay, so I'm not sure why it's like that in my math lab, but it's the same thing as what I got. Okay, what about the second question? Now, the second question is much more difficult, I think, and I think it's kind of a subtle thing to understand. It says, suppose we walk 3 miles an hour. Okay, so from here to there, we're going to walk 3 miles an hour. That was actually the scenario from the beginning, that we walk at 3 miles an hour. Okay, what is the minimum speed that we would have to row so that the quickest way to the restaurant is to row directly? So say you can walk at 3 miles an hour. What's the minimum speed you have to row to make walking unnecessary to minimize the travel time? Okay, that to minimize the travel time, the way to do it is to not walk at all, to row directly from start to end. As it is, if I row at 2 miles an hour and I walk at 3, I'll need to land somewhere on the shore to minimize my travel time. But it could be that if I row fast enough, walking becomes unnecessary. All right, so think about it like that. So let's do this. Here now, this I think is kind of a subtle thing. I try to explain to you what we're getting at in that second question. But I'll say it like this. So say the row speed is, we don't know. We're trying to figure out what the row speed is so that walking is unnecessary. Okay. So I'll say solve for the row speed R. We'll call it R. So that critical point, all right, t prime x equals 0 is under the condition that x is 7. Why would I say that? Well, if x is 7, then it's like we found our answer to be that this point is over there. It's at the end, okay? All right, because what if you solve this and we got 7 right there? It would mean this length here that you walk is 0. All right, so that's what we're after. That's the rationale for me wanting to do it this way. So here's t prime x. Now notice where I put the r like that. So I'm just saying that if I had my total time function and that speed that we row was r right there, this would be an r. And when we went through this process of finding the derivative, that would be r. This 2 and that 2 would cancel. So it would be x over r root x squared plus 25 minus a third. So there it is. That would be your derivative. Now, this, under this new scenario, t prime x would be 0 if x is, if x is 7. Okay, so this is our derivative. It would be 0 if x is 7. That's where we would find our solution. All right, so I put 7 in. That leaves me only r to solve for, and I'll get 21 over root 74. So if this was the row speed, then we can't minimize the travel time any further by picking some point to land on the shore. If the row speed was slower than that, then there'd be some point to land at the shore and walk the rest of the way that would minimize our travel time from there. Okay, so that's how we find the second answer right here. Now, I do think still that this second question and answer and the way you go about it is kind of a subtle thing, so I'll explain a little bit more. Actually, this function that measures the total travel time is on a closed interval. Like the x, I mean, it doesn't make sense that the x to be just anything. The way that I've conceived it, that distance right there can be anywhere from 0, which would mean we row straight to the shore and walk from there, or it could be 7, which means we row straight to the restaurant. So this function is defined on a closed interval. 0, row straight to the shore, x, straight to the restaurant. Now, it turns out if r is 2, like in the original scenario, then the minimum, the way to minimize that total travel time is somewhere between 0 and 7. Okay? We found it at 2 root 5. That's the spot where the derivative is 0. Your critical number is there in the middle. And if we were to check the endpoints by comparison, which I guess technically we'd have to do if the function's on a closed interval, then that minimum does occur somewhere in the middle. It dips down to a local minimum, somewhere in there. Now, what we're actually doing is thinking like this. If r becomes gradually and gradually bigger, here's what happens. This minimum point gets pushed that way. It gets pushed to landing closer to the restaurant. It gets pushed to walking less and less. So it's like we're taking this curve and r is modifying it such that we're pushing this minimum all the way over there, and then there's not a critical number in the interval 0 to 7. The critical number is actually at the end of that interval where it's 7. So this like low spot, this flat point gets pushed all the way over there. And then so we're finding the r that way. Okay, so that's why we get this condition that the row speed r is such that the derivative is 0 if x is 7 at the endpoint. All right, x being 7 indicating we row straight to the restaurant, and then that's where that critical number is. It's not somewhere in the middle. Okay, all right, so that's how you can think about it. I hope that's not too subtle, but if we put the conceptual parts aside, I think the math in this one is like a lot of the other questions.